So today I will speak about improving the approximability window of a scheduling problem, which happens to be on hybrid platforms. This is a joint work with Vincent Fagnon, Imed Kacem, and Giorgio Lucarelli, and I am Bertrand. So our goal is to schedule an application on a computing platform, and we will see this application as a graph of tasks, so as a DAG with a precedence constraints, and we are aware of the durations of all the tasks. So then we want to complete this graph as soon as possible, so which is known as minimizing the mixspan. So now that the model is clear for the application, we still have to model the computing platform. And one of the many classic ways to model it is to just assume that our platform is composed of m identical processors. But the issue with this classic model in my talk today is that I want to focus on the use of accelerators, such as GPUs, which happen to be more and more present in today's computing platforms. And so we want to target how we should use them as efficiently as possible. So then the second really general classic model that we could use, we'll just assume that we have m totally different processors, but it is a model which is way too complex, and it's impossible to design good algorithms and simple algorithms in this setting. So therefore, I will speak today about a more recent model, which assumes a more realistic type of heterogeneity. And we will just assume that we have two types of processors. So we will not really distinguish them, but we'll still call one of them as CPUs and the other one as GPUs. This is the main motivation for this model. So now we'll define our problem formally. So we are given a graph of tasks with the precedence constraints. So you cannot start a task before its predecessors are terminated. You have m CPUs, which are all identical, and k GPUs, which are all identical. And we will assume, with a clause of generality, that m is larger than k. For each task, we know its duration on CPU and on GPU. And the goal is to schedule this graph of tasks while minimizing the mixspan. And we will ignore communication times between CPUs and GPUs and in between GPUs in this context. So we will evaluate our algorithm by the classic metric of approximation factor, which means that we want to minimize the maximum value over all instances of the obtained mixspan divided by the optimal mixspan for this instance. And I will note that this model has been used for several years already in other contexts, such as independent tasks or where tasks arrive online. But here we focused on the offline model, where we know everything in advance and when we have the precedence constraints between the tasks. So we'll first give some intuition about this problem before presenting our results. So we can see this problem as two subproblems. The first one, which we'll name the allocation subproblem, is the problem. So for the first one, we want to decide on which processor type, so either on CPU or on GPU, we'll place each task. And once this allocation is decided, then we have to schedule these tasks, so to decide when each task is run. So if we just focus on the second subproblem, and we assume that by some oracle or by some other way, the first subproblem is already solved. So we have an allocation of each task to a type of processor. Then the problem is quite easy. As a simple algorithm, which is known from decade, which is list scheduling. So list scheduling simply executes a task as soon as possible if there is a processor which is available to run it. So we never let a processor idle if we can avoid it. And this algorithm is actually the best known algorithm for this problem. In order to analyze it, we can define some quantities once the allocation has been fixed. So we define WC, which is the total load on the CPUs, so which is the sum of the processing times of all the tasks that have been allocated to CPUs. WG is the same for GPUs. And CP, which is the length of the critical path. So this is the length of the longest path in the schedule. So it's basically the time that we will need to complete the graph even if we had an infinite number of processors of each type when the allocation is fixed. And these three quantities are actually related to the performance of list scheduling and to lower bounds on the optimal schedule. And we can extend the classic result by showing that list scheduling is a two approximation when we have only one type of processors to this lemma here, which say that the max span that we obtain with this scheduling is at most the critical path plus the average load on CPUs plus the average load on GPUs. And each of these terms is a lower bound of the optimal max span. So this means that list scheduling is a three approximation if the allocation has been fixed. And so we now present the approximation window, which gives the title of this talk. But I will first focus on the more classical model in which all the processors are identical. So let's say that we only have CPUs and no GPU. So here, the best algorithm which is known is the one I just presented, list scheduling, which is a two approximation. And the best lower bound that we know is that getting an approximation factor which is smaller than 4/3 is NP-hard. And for several decades, there have been no improvement in this gap here. And we didn't know if we could improve list scheduling or if we get better lower bound. Until Vincent in 2010 used a variant of the unique games conjecture to show that improving over list scheduling is NP-hard if we assume this variant. So this showed that in this kind of problem, we still don't really know how to get proper lower bound without having other conjectures than P is different than NP. And we will see that this is also the case in our exact problem. So if we get to two types of processor, the positive result do not hold, but the negative result still hold. And the best algorithm, which dates from 5 years ago, is a 6 approximation. And this factor 6 comes from a factor 2, which is the integrality gap of a linear program, which is used to decide the allocation of each task, multiplied by the factor 3, which comes from list scheduling. And so now, one result of our paper has been to improve the conditional lower bound from 2 to 3 in our model by assuming a stronger variant of the unigames conjecture. And this is also true if the allocation subproblem is already fixed. So this means that list scheduling is actually the best algorithm we can do if the allocation is fixed, assuming that the conjecture is correct. And this also means that the factor of 3, which appears in the previous algorithm, actually cannot be improved. And we also know that the factor of 2 for the LP cannot be improved because it comes from the integrality gap. So we could think that this algorithm was actually the best solution possible. Nevertheless, we have shown in this talk that we can actually improve over this algorithm by using a rounding of the linear program, which is in a sense worse. So we will lose a factor which is larger than 2, but then we will gain on the structure of the solution that we built in order to use to improve over the analysis of list scheduling for this specific graph that we will obtain. And therefore, we can improve from 6 to 3 plus 2 square root of 2, which is around 5.8. So now at the end of the day, what remains is this blue gap here. And if we assume that the variant of the UGC is true, then the big question is how much do we lose when we have to decide for the allocation subproblem? So I will now present the 6 approximation algorithm, so which is from 5 years ago. So as I said, we first want to round a linear program to get the allocation, and then use list scheduling to get the schedule. So the linear program is sketched on the left of this slide. So we want to minimize some quantity C, which is defined as a maximum between the average load on the CPUs, the average load on the GPUs, and the critical path. So all of these three terms are lower bounds of the optimal solution if the allocation is fixed. And in order to express this as a linear program, so it's shown on the right here, but I don't want to go into the details. So we just need to know that in order to express it, we need to use one decision variable for each task, which is equal to 0 if the task goes to CPU, and to 1 if this task goes to GPU. So then, as we want a polynomial time algorithm, when we solve this LP, we will get a fractional value between 0 and 1 and not an integer value. So we have to run this LP in order to get a proper allocation. And this is what is done on this slide. So when for each task, we get some value which is between 0 and 1 on the top here. And the rounding that was applied in the first algorithm is quite simple. So if this value is less than a half, we do as if this value was equal to 0. So we put this task on CPU. And otherwise, we do as if this value was equal to 1. So we put it on GPU. So then, if we use the bound of the list scheduling, which I presented before, we get that our max span is smaller than this quantity here. And by studying the math, we check that we can replace each term here by the fractional optimal solution multiplied by the factor 2, which we lost by doing this rounding. And once we sum the 3 factor 2s, we get the 6, which is the approximation ratio of this algorithm. So this is, in a sense, tight in two ways, because this factor is rich on an example, so we cannot improve this proof. And the LP integrality gap is equal to 2, so you cannot improve over this factor 2 here in all of the terms. However, we have proposed in this paper a rounding which is, in a sense, better. So we pick a value b which is larger than 2, and which will be fixed at the end of this slide. If a variable is small enough or large enough, we do the same as before. But if it's close to a half, so namely between 1 over b and 1 minus 1 over b, we will put this task on the fastest processor. And this way, we will gain when we want to bound on the critical path, because instead of losing a factor 2, we will lose this factor, which is less than 2, because we make the correct decision if the task is close, if the value was close to a half. But on the opposite, we will lose when we want to bound the loads. So when we want to bound the average loads here, we will use a factor b, which is larger than 2, because we may make the wrong decision in the middle section here. However, the main idea of this algorithm is that we can bound the sum of the total load instead of the sum of the average load by a factor which is smaller than 2. And then we make this term appear in the bound of the max span. And when optimizing and doing the math, we get something which is better than 6 at the end, so which is 3 plus 2 square root of 2. So now say a few words on the second result, which is the conditional lower bound. So here we have the same assumption as a paper from 5 years ago, working on related processors, which uses a variant which is a bit stronger of the unigame conjecture than the one that was used 10 years ago when this variant was first related to scheduling problems. So our lower bound stays valid if the allocation is fixed, as I said before. It also stays valid if the processors are related. So for instance, if all GPUs are twice faster than CPUs. And it also stays valid if the processors are unrelated and for any value of m over k. So when m over k, the ratio of the number of CPUs divided by the number of GPUs. And this is interesting because this ratio is linked to the difficulty of the online problem, where the best algorithm is in square root of m over k. And then we can also plot the approximation window that I shown before in function of this value of m over k. So here on the y-axis, you have the approximation ratio. On the x-axis, we have m over k. We have a gray area below 3 because our lower bound forbids any algorithm to be better than 3. The algorithm that existed before is the blue line here at the top. So it's a 6 approximation for every value of m over k. And our algorithm here is this red line. So I have shown that the maximum value is around 5.8. But actually, you can also improve it when m over k gets small. And when m is equal to k, we actually match the lower bound of 3. But still, we can see that there is some improvement to be made in this problem. Because if we take the simple online algorithm, it has a complexity, an approximation factor ratio of 2 square root of m over k plus 1, which is large when m is larger than k, but which is still better than our algorithm for small values of m over k. So this shows that there is some room of improvement still to be made here, which could give some intuition in order to get a better approximation ratio overall. Thank you for your attention.
And are there any questions? Remember that you have to close the screen and come to the mic. Okay, if not, no one is coming. If not, then I have one question. I mean, what about 3 kinds of processors instead of having a GPU, a CPU, perhaps another kind of CPU? I mean, can you kind of extend your algorithms, this notion of 2, 1/2, you use GPU, and so on?
Yeah, so for the negative result for the lower bound, it will hold, and you will get, if you have 3 types, you will get a 4, a lower bound of 4. If you have 4 types, you will get a lower bound of 5, and etc. So you add 1 each time you add a type of processor.
Yeah.
For the positive results, the factor of 6 can be improved to the number of types multiplied by the number of types plus 1. So for 3 types, you will get 3 times 4, so which is 12, which is quite large. And we still don't know how to improve over this for a larger number of types.
Just for 4?
I'm sorry?
Just to 4 kinds of machines?
No, we can get it for any number of machines.
Any fixed?
Yeah.
Okay, thanks. Thanks. Very nice. If anyone has any more questions, we can discuss on the Q&A session later.